So we'll get started in maybe 2 or 3 minutes.
Yo, Pranay, where's the option to have the background? I can't find it.
You go to the where you share your you start your video and then you
Oh,
click
got
the
it.
arrow.
Yeah, thank you. Um,
Just wait for a few more minutes for anyone to come in.
okay, apparently my computer can't do it, which is stupid. So I guess we'll stick with this for now.
Maybe 1 more minute. Okay, I think we'll get started. Henry, do you want to start us off?
Yeah, I'll start now. We have everyone in from the waiting room.
Yeah.
Cool. All right. So hello everyone. Welcome to our presentation. We are Team Juice, and today we're going to be going over drivetrain design, the basics. My name's Henry. I'm the team captain of Juice.
I'm Pranay. And and then we also have Abid and Arnav who will be talking about drivetrain as well. So here's what we're going to be going over in this presentation. So the first thing to start off with is, of course, your wheel varieties, and then how you get power to the wheels, so your power transmission, the basic drivetrain terminology, and then the common drivetrain designs that you normally see in FTC. And then if you're just starting out, then some kits that you can buy to assemble your drivetrain, as well as some custom solutions. And then we'll be going over 16236's drivetrain from last year, and then analyzing it to see what we did right and then what we could improve on for the next season, just to give you guys an idea of how we would go through the design process. So this is us. We're from Northern California, and we were lucky enough to go to regionals and be part of the winning alliance. And yeah, so that's about us. And then first we'll start off with the wheel varieties. So what are the main kinds of wheels that you see teams using? So the first off, we have the stealth and the traction wheels. So as the name suggests, they have good traction with the floor mats in FTC. And what this allows you to do is have very little slippage for your robot in the ground, so that you can be accurate and not be sliding around the field. And then next we have the Omni wheel. And the special things about these wheels is that they, as you can see, they have those perpendicular rollers. And what this allows you to do is that if you orient the wheels in a particular fashion, then you can achieve omnidirectional movements, which means the movement in all directions. Next up, we have the Mecanum wheels, and these are probably the most versatile wheels that you can get. So as you can see, they have the rollers at the 45-degree angle, and if you independently directional movement. And then Abid will continue with the power and transmission.
So let's talk about power transmission or getting power from the motor to the wheels. Sorry about the noise. Um, okay. So
Abid, do you want me to cover this first?
yeah, do that.
Cool. So, of course, in the drivetrain, you will use your motors to provide rotational motion. The two most common variants of what we call gear motors that you'll find are spur and planetary. And so basically, these names refer to how the axle is oriented on the output of the motor, because almost all the motors you will use in FTC already have a gearbox attached to them. And so in a spur gearbox, the axle isn't centered, but it's actually offset to the side. And this is really useful for chain tensioning, which Abid will cover a little bit later. So basically, you're just changing the distance your motor axle is from your wheel when you rotate the motor itself. And then the second option that you have is planetary, which is where the axle is centered on the output. And this is generally more sturdy and efficient than a spur gearbox. In a competitive team usually uses 4 motors on their drivetrains for maximum power. So we really recommend that. And the thing you want to keep in mind when choosing motors is that gear ratio is extremely important. And so usually a good starting point teams go from is a 20 ratio, also known as 19.2 if you're using the Go Build a system. And this is really good for robots using 4-inch wheels. And so the general rule of thumb is the lighter your robot, the higher of a ratio you can go to. But if your ratio is too high, your robot will not be able to accelerate to its full speed quickly enough, or it might not even drive at all. And so some recommended brands that we use for drivetrain motors would be the Go Build a Yellow Jackets, the Andy Mark Neverrests, and the Rev HD Hex. And in the next slide, we'll show some examples of those.
So as you can see on the left, those are the, so these are all planetary motors. So as you can see on the leftmost one, that's the Go Build a Yellow Jacket. And in the middle one, that's the Andy Mark Neverest. And then over here, you can see the motors that are Rev events. So you can see they have the planetary option as well as the spur options. So generally, depending on the weight of your robot, choosing the gear ratio is especially important. So a 20 to 1 ratio would work for almost any robot, any weight. And then if you're on the lighter side, or if you're using smaller wheels, then you would want to decrease that ratio, and so that you'll have a higher output speed. So then you could go down to 13.7 or somewhere around in that range. And then if your bot's a little heavy and you're having a hard time getting enough torque to move your robot, then you would go on to the 26 to 1 ratios or even higher, depending on what your robot needs.
And just a quick note to include, the 13.7 and 26.2 ratios are only applicable to Go Build It, which has a wider variety of ratios than other ecosystems. Andy Mark and Rev only have 20 and 40. So that's just a quick note to throw in if your team happens to use different building ecosystems.
Andy Mark also has 3.7s, but those are a little low for drivetrain purposes. So Abid will continue with the different kinds of transmission.
So getting the power to the wheel, there's many different ways to do that. One is direct transmission, which means the wheel is directly attached to the motor. This has a few disadvantages, as you cannot change the gear ratio from the motor, and it'll bend your motor shaft if something hits the wheel, which happens more often than you think. It does simplify the drivetrain, as it does not require gears or anything else. So the next type is gear transmission, which is a very reliable type. So the most common are spur or straight cut gears, which are nice because it makes adjusting gear ratios very simple. We need to maintain proper distance between the gears. There are also bevel gear systems, which are two gears that combine to make a 90-degree angle. So you can have the motors in many different positions. Gears are also used for adjusting ratios, like a small to big gear would give you more torque than you would get from a motor, but a big to small would give you more speed. So the next one is chain transmission, which is used for moving the power long distances. So for example, if your motor is far away from uh, the wheel, because that's the only place you could fit it, then you use a chain. Chain, if done properly, can work just as well as gears, but normally they have problems like stretching and needing constant maintenance like tensioning. Tensioning is very important in chain and belt systems as it ensures that the system is running at maximum efficiency. Chains can also do gear ratios if you change the sprocket sizes on the ends.
So as you can see in this picture, this team actually used both bevel gears and the chain system so that they could have a lot of interior space on the robot, and their motors are outside of the middle when they do this. The motor here, I believe that's an Everest 3.7 to 1. And then you can see that they have a bevel, and then the bevel is attached to a chain, and then the chain finally goes to their wheels. And next we have belts. So like chain, they're used for long distances. Um, and if you get perfect center to center distancing with the belts, then you generally don't need to maintain them. And then you can see in these pictures right here, they have the motor, and then there's a belt pulley on it, and then that's attached, and then there's another belt pulley attached to the wheel, and then they have the belt running in between them. So I'd say from personal experience that the belts are a lot less problematic than uh, chains are, but then the only disadvantage is that uh, the belt system is a lot bigger and wider than the chain and sprocket system.
So this is an example of a belt drive from the World Champions gluten-free. You can see how the belt has a perfect center to center distance from the motors in the middle all the way to the wheels on the end.
Sorry, I was muted. Next, we're going to dive into drivetrain terminology. So what are some key drivetrain design terms and their pros and cons? So the first term we're going to cover is cantilever, and this is a term to describe when your drivetrain wheels are supported on only one side and left exposed on the other side. So as you can see here on this Strafer kit by GoBuilda, the wheels are only supported on the axle from the channels that are on the inside of the robot, and there's nothing holding it on the outside. What are the pros and cons of this design? Well, clearly cantilever is a very simple design, and the wheels are easy to access if you need to do maintenance or add something, and it saves weight because an outer plate is not needed. However, some cons include that your space is limited on the where the wheels are. So if you want to mount stuff towards the outside perimeter of the robot, you may be limited there. In addition, your wheels are not protected from defense or running over game particles, and you can put heavy loads on the wheel axle if not designed correctly. Since the engineering terminology of cantilever is that you are only supported by one side, the further away your wheel is from the base of your robot, the more strain you will put on the axle. Moving on, we have parallel plate, which is where you use a custom frame or a pattern plate to hold wheels and power transmission in the middle. And so the way that you would design this is that you have your inner plate and your outer plate, and then you sandwich your wheels and your motor as well as your power transmission in the middle, creating what is called a drive pod. So as you can see here in these two examples below from teams Curiosity Robotics and Recharge Screen, Curiosity Robotics chose to pattern their inner plate so that they could attach more components to the inside of the robot. And they removed sections of their outer plate to save weight and allow easy access. And this process is called pocketing. You can see here that Recharge Screen also pocketed their outer plates by cutting out some triangles and rectangles.
So this is a comparison between a cantilever and a parallel plate with using the Go Build Kit. So as you can see here on the left side, that the power transmission is kept on in between these two channels here, and then the wheels are left exposed are only supported on one side, left exposed on the other. Whereas the wheel is being held on both sides with these channels on this right side here, and the power transmission is more on the exterior of the robot. And then you can see how this large gap in between the wheels on the left one, it can't be really utilized effectively unless you build something else on top of it. But then here you can have stuff on the very side edge of your robot in case you needed it. And then this is usually when people try to do parallel plates, they would go to the custom machining route. But then this right side is a good example of how you can still stick to using kit parts and build an effective drivetrain. And Henry can continue with the pros and cons of parallel plate.
Right. So there are a number of reasons why you would use parallel plate instead of cantilever and vice versa. So the first pro is that clearly it's very sturdy. You also have a lot of design flexibility because even if you're using a pattern plate, both a pattern plate and a custom cut plate will offer you a lot of flexibility in how far you want your wheels to be apart, where do you want to have mounting capability, where do you want to mount your motors. So you have a lot of you have the ability to modify your design a lot however you like. Of course, the outer plate also protects your wheels and power transmission from defense or like being hit by game particles, and it does look really cool. However, some cons of using parallel plate is that it can get pretty heavy since you have an extra outer plate on both sides of the robot. And in addition, space between interior plates is limited. So because you have these two plates sandwiching your wheels, motors, and power transmission, your space in between the drive pods, the crossbeam space can be limited. So if you're trying to like intake something big, that can cause problems for teams. And in addition, generally it requires an ability to CAD, access to fabrication, and more lead time. This is because most teams that do parallel plate opt to create their own custom plates, but as we mentioned beforehand, it is completely viable using just kit pieces such as pattern plates. Moving on, we're going to discuss axle variants. So there are three main. So
yeah,
Renee, go ahead.
Okay, so there are three main types of axle setups that people use in FTC. The first one being live. So what this means is that it's like your traditional axle setup where the motor output is on the axle, and then the axle is clamped to the wheel, which therefore spins it as you apply power to the motors. But then another common way of doing power transmission is by doing a dead axle. What this means is that you have a stationary axle going through the wheel, and then so it's stationary, it doesn't move, and then you have some sort of power transmission like a gear or a sprocket or a belt pulley attached to the wheel itself, and then you insert bearings into the wheel. And what this allows you to do is that even though the axle is stationary, the wheel can still turn around the axle instead of the wheel turning the axle, if that makes any sense. We'll show a simulation of how this works after I explain zombie axle. So zombie axle is essentially like live axle, except but it also has some features that dead axle uses. So in zombie axle, you attach the power transmission method directly to the wheel like this, but instead of having the bearings inside of the wheel, you have the bearings on plates, and then you run a live shaft through that and clamp it to the wheel. So, and then you might ask, like, why would you ever use zombie axle instead of dead or alive? So what teams like to do is have a sense of redundancy, so that just in case one part of their drive fails, then they'll have the extra redundancy of having the bearings on the outside. So it's just more of a peace of mind situation. So here I can show you an on shape that we have. One of my friends actually made this this document to showcase the differences between the three types of axles. Wait for this to load up. This one
We'll
might
cover
be, yeah.
Onshape in the second part of the presentation and why you should use it as a great CAD software.
Okay, this is taking a while, so we'll come back to it at the end of the presentation. So this is like more of a chart of like the differences between the three types of axle configurations. So in live axle, the axle is moving, and it's directly powered by chain, gear, belt pulley, and the wheel is clamped to that axle, which allows it to spin. And then in dead axle, the axle is not moving, but then there are bearings and your power transition method directly attached to the wheel, which allows the wheel to spin around the axle instead of this axle spinning the wheel. And then you look at zombie axles. So the axle is moving, but the way that the axle is given power is from the wheel. So the wheel is clamped onto the axle, but the method of power transmission is attached directly to the wheel. So Arnav can talk about the common drivetrain designs in FTC.
Okay, so how do we put this information into a drivetrain? Let's look at some common types. So the first type is the tank drive. It is probably the best and simplest FTC drivetrain. The most common variant of this style is the 6-wheel drive. One downside is that this drivetrain cannot strafe though. However, because the traction wheels have a lot of friction with the ground, the bot won't be pushed around by other bots. Some teams often use a drop center design where the middle set of wheels are lower than the rest by about 1/16 of an inch. This means more weight on the center wheels for easier turning due to less resistance, which means 4 contact wheels instead of 6. Using omnis on the corners improve turning as well because they have less resistance with the ground as compared to stealth and traction wheels. A live axle is an axle that not only connects but also transmits power to the wheels. And so as you can see, Team 7244 and Team 10320 both utilize a live axle system.
So this is kind of a demonstration of the drop center that Arnav was talking about. So you can see that the center wheel, which is represented by this dotted circle, is about 3 millimeters lower than the other two wheels. And then this will create a rocking effect where the bot will actually be pivoting on that center wheel. And depending on how the weight is distributed on the robot, then there'll only be 4 wheels in contact with the ground versus all 6. And this will gives you less resistance and allows for easier turning. And then we'll share this presentation with you after this, so you guys can watch this video of how the robot rocks back and forth on that center wheel.
Okay, so H drives are like a tank drive with a perpendicular omni wheel setup. This permits the ability to strafe, however, can be problematic as the center wheels may not be always in contact with the ground. So as you can see, Team 15682 and FRC 148 both use a live axle system.
Yeah, so you can see on the photo on the left that they have the 4 omni wheels set up in the corners, and they also have that middle omni wheel that you can kind of see right there. So and that's the special thing about omni wheels, is that they have those perpendicular rollers. So when that middle wheel spins, then the whole robot can move sideways because the rollers on the corner wheels are spinning with that perpendicular center wheel.
Mechanism drives, or holonomic drives, are the most versatile drive systems because each wheel is independently powered. This allows the robot to move in any direction without altering the orientation of the robot. A possible downside to utilizing mechanism drives is that mechanism wheels are quite expensive and sometimes over $100. And as you can see, Team 731 uses a dead axle system, and Team 6710 uses a live axle system.
Another downside of using mechanisms or the omni wheels in the H drive is that they introduce a lot of slip. And what this means is that if you're trying to program your autonomous, then it introduces inaccuracies as the the motor encoder output will not match where the robot actually is. And then here you can see the GoBuild strafer chassis once again, and how you're supposed to orient the mechanism wheels so that you can achieve all sorts of omnidirectional movements.
Now we'll discuss some common kits and materials that teams use to build their drivetrain.
Starting off, we have GoBuilder and its imperial equivalent Actobotics. So these systems have become very popular because they have a very extensive part catalog, and a lot of teams are shifting towards GoBuilder now because it has a very versatile hole pattern and it's metric versus Actobotics, which is imperial. They're both made by the same parent company, Servo City, and we'll show you. Yeah, so here you can see that the picture in the top right here, that's the GoBuilder pattern, and it's based on M4 screws, and it's on an 8mm grid. And then these center holes here are normally used for bearings or other motion components. And then again, you can see the strafer chassis here on the left. And on the bottom, you can see that 12x power pattern. And it depends on the team's preferences. I know that Active Robotics is a little smaller in terms of form factor than GoBuilder, but it's really up to what the team decides to go with. And then Henry can talk about the Rev system.
Yeah, so Rev Robotics is a great alternate system to GoBuilda and Actobotics. The main difference between Rev and GoBuilda/Acto is that it uses mainly extrusion as opposed to channel for construction. And as Pranay can show in the next slide, extrusion is generally a long bar where there is slots running down the sides, and teams can slide in screw heads into those slots to mount their parts wherever they want. And so, as you can see here, just letting it load. You can see down here on the bottom left, that's an example of 15mm extrusion, which is what Rev usually uses. So as you can see in the photo of the robot next to it, this is from Team Quicksilver. They used extrusion on the bottom frame of their robot to hold their drivetrain, and their mechanism wheels, which are a little hard to see, but they're in there, are sandwiched between the extrusion, and they also use short extrusion pieces to mount their side parts together. And so going back to the previous slide, the advantage of this is that you have unlimited mounting opportunities, which can be really useful for drivetrains if you're trying to like make your chain stretch out a little bit more. You can just slide that screw head a bit further along the extrusion. The downside of this is that extrusion is generally a bit weaker than U channels and C channels for construction. And the other thing about Rev is that its brackets, wheels, and gears are generally smaller and weaker. However, this is still a great system for rookie teams transitioning from FLL.
Yeah, and what we really wanted to push forward with this presentation is that no matter what kit or building system that you use, you can still be very successful and still have a very competent robot. And then, so I'll talk about some custom materials that teams use. So if you're a rookie team and you don't have or you don't have a lot of access to resources, then I would suggest that you would stay more to the kit side, because obviously you don't need access to expensive machines or material in order to construct the robots. Anyway, so a common material that teams use is aluminum, and we in fact use water jetted aluminum to build our drivetrain plates. We used the 6061 T6 alloy, which is very easily machinable, and it's very accessible as well. And then there's plastics to construct the robots, which is weaker than aluminum, but you can compensate for this by using slightly thicker sheets. So you can use some plastics that teams use are Delrin, which is acetal, as well as Lexan, which is polycarbonate. And yeah, so you can see here that you need to buy a little bit thicker than the aluminum, just because aluminum is obviously stronger than plastic. And then you could use a laser cutter or a bandsaw to cut these plastics, but it's generally not recommended, as they're obviously not. So the bandsaw is definitely not as accurate as like a CNC or a water jet. And then some plastics are kind of dangerous to cut on the laser cutter because of the fumes that it produces. And then another material that teams can use are 3D printed parts. So these are very useful for like the small pieces that you won't be able to machine out of a sheet or from a kit. And these you could create things like belt pulleys, phone mounts, those kind of things using 3D printed material. And then generally teams like to use PLA or PETG filament, as they're relatively easier to print than other filaments, and they're pretty robust. So then now we'll look over our design from last year, and then we'll go over why we did what we did, and then what we would like to change for next season. So you can see that we made all these CAD drawings on Autodesk Inventor, and we'll talk about CAD in a little bit. And then we made sub-assemblies for each part of our design. And this is important because say you're CADing and then you screw up one sub-assembly, and so then you can change that sub-assembly instead of having to change the entire robot assembly. So it just makes your life a whole lot easier in case you make a mistake. And then here's some renders of our bot from last year. And then, so if you're talking about our design specifically, you can see that we have our motors in these go build axle setup. So what this means is that we had a standoff connecting from one plate to the other, and then we had a bearing inside of the wheel, and then these motors are the Go Builder 19.2 to 1 yellow jackets, and also this is also a parallel plate design. So in order to make use of this space that's created, we created these top plates here with the Go Builder pattern on it, so that we could mount different things to it, like our phones and other components.
Yeah, so now we'll cover some pros and cons of this design and a reflection of what we would have done if we were to do this again. So first of all, we've discovered afterwards that our pattern on the inner plate was not CADed correctly, and so we had to spend a lot of time remachining that. So it's just always make sure to double check your CAD before you before you get stuff manufactured. And we also found that the outer plates could have been pocketed even more to provide more access to key parts such as our wheels and gears. Pranay also mentioned that our motors were inside the crossbeams. From our personal experience, we do not recommend teams nest their motors in their crossbeams because you effectively cannot mount anything to the crossbeam because the motor is blocking access to the inside of that crossbeam. Instead, what you want to do is put your motors outside of the crossbeams and leave the interior of the crossbeams open. In addition, something else that we didn't that we should have not done is that we mounted our rev hubs in the middle between the two crossbeams. And so while this might seem like a great place to put your rev hubs out of sight, this is actually a terrible design choice because all of your wiring for the rev hubs is going to like sprout up and get messy all over the robot. And the last thing you want in a competition is to have tangled wires being caught on stuff. So if we were to do this again, obviously we would take our motors outside of the crossbeams. And since the motors would be in a different place and not as close to the wheels, we would use belt to transmit the power instead of gears. And then back to what I was talking about, the rev hubs, we would probably put them on the side so that they're easier to access and so we can pull out and plug in things far easier. And those are just some reflections we had about this design. And one good thing that one part of this design that we felt was a strength was that we used the Go Build a 12mm Rex as a dead axle system. And that worked really well because it acted as both a standoff to connect the plates and as an axle for the wheel.
So that's it for the drivetrain overview. So now we'll be going over some basics about CADing in FTC. So Abid can take over from here.
Sure. So the first step in making a drivetrain is to CAD it. But what is CAD? CAD stands for Computer Aided Design, which means exactly what it says. Use a computer to help you model your design. But why use it? So according to Game Manual Zero, which is a great resource for FTC, you should check it out. CAD is beneficial for two reasons. One, it solves a lot of preventable headaches like spacing issues. So it'll save time when you discover problems in CAD that you can remediate before you build your robot. Also, CAD is a professional tool that's used in many STEM fields, and having knowledge of this will be beneficial in your career in STEM. So how do we use CAD in FTC? We can use it to, one, design our robots, thus, like we mentioned before, eliminating problems before they appear, like spacing issues. And the second way is we can machine custom parts, like we CNC a drivetrain plate based on our needs, based on our CAD. CAD's also great for the engineering notebook, like renders, which judges love, and also helps explain the engineering process. One of the best things about CAD is 3D printing. CADing custom parts to print is necessary for all teams, from slide inserts to odometry pods.
So these are the four main softwares that teams generally use that we recommend that teams use. So the first one is the one that we use, which is Autodesk Inventor. And this is a pretty versatile system. It's available only for Windows. So if you have a Mac, then then another great software to use is Onshape, because this Onshape actually runs on your browser instead of like a application on your computer. And then it's also great for collaboration, as you can really easily share part files with your team, and you can do live editing with the group, and it's just overall a really great program. It's also very beginner friendly. And then we have Fusion 360. So this one requires a little bit more expertise, but it's just as capable as any of the other four. And as an added bonus, has a very good rendering engine. So if you want to create some really nice renders of your robot and your designs, then highly recommend using Fusion 360. And then now we come to SolidWorks, and then SolidWorks is probably the most complex, and it can pretty much do anything that you want it, as long as you know how to. and it's available for PC. And it also has its own very good rendering engine called Visualize. So if you're a beginner team, I would recommend using Onshape just because of how easy it is to use and to collaborate. But there's no harm in learning all the other three and then having an expertise, not only for FTC, but also for your future. So what are the differences between these four programs? So as I mentioned about Onshape, that's very beginner friendly, collaborative, it's easy to learn, and it's all based on the cloud, and it's on your browser. So you can just open Chrome and open Onshape, and you can make edits to your parts. And then next up is SolidWorks. So SolidWorks is used heavily in the industry, and it's a very good tool, very versatile. The only downside is that you need a good system. You have to have good specs on your computer in order to run it, and also it's a fairly advanced program. So you would need it's not something you can just like pick up and like figure out. You need to like look at tutorials, or you have to go to classes in order to learn SolidWorks. And then next we have Autodesk Inventor. So Autodesk is pretty similar to SolidWorks in terms of capability, but the advantage of it is that it runs better on a lot better on low-end PCs and relative to SolidWorks. So if you don't have the greatest computer in the world, then you can run Inventor on it for sure. And then next we have then we have Autodesk Fusion. So it's basically like a cloud-based Inventor, and you can store all your files in the cloud, and as well as do your rendering on the cloud. So if you don't have the greatest graphics card, you can still produce very high-quality renders. It has a simpler UI than Inventor and SolidWorks, and as I said before, it has a really great rendering engine.
So you want to learn CAD, but where do you learn? So the best place to start is YouTube. Many other FTC teams have CAD tutorials, but any tutorial specific to your program will work fine. You can also go to the CAD websites and search for help, such as Autodesk University and Onshape, as they have many tutorials. Registering for online courses might also be an option. However, some may cost money.
So Henry can talk about how we used CAD in the past season.
Yeah, so as we mentioned before, we did a parallel plate design for our drivetrain, and we opted to have these plates custom machined out of 1/8 inch aluminum plate. And so, of course, in order to machine these plates, we had to first design them in CAD. And so, as you can see here, this is a what we call a DXF file, or pretty much just a outline of our outer plate design. And we also used CAD for a lot of our intake and decorative parts. So what we actually did was that we made a copy of our outer plate, but in gray polycarbonate, and we attached that on the outside of our robot as a place to attach our team number stickers. As you can see here on the right, we also had our claw intake from last season, and you can see the 3 plates there with the holes through them. Those were the plates that grabbed the stones, and we also CAD'd them using Autodesk Inventor and had them custom machined for us. And so apart from plates, CAD's also great for 3D printing, as Abid mentioned earlier, because with 3D printing, you can pretty much have unlimited potential for small parts that you want to make.
So, and you can see right here, these orange servo mounts that we 3D printed. So there's a lot of possibility for CAD and 3D printing especially.
We use CAD primarily for custom 3D printed parts, such as slide inserts, phone mounts, and other specific parts such as odometry pod inserts.
So yeah, you can see here that these are our 3D printed servo mounts. Here's our phone mount. And then these white plates here for our odometry were also 3D printed, as well as our SAR 230 slide inserts. So that's it for our presentation. If you have any questions, please leave it in the Slido. I think Heather put the Slido link in the Zoom chat. And then right now I'll see if I can open up that Onshape document that I was trying to do earlier. Okay, here we go. So this was in reference to the axle setups. So this is an example of a live axle. So if I can orbit, so you can see here that there's a small hub right here that clamps the wheel to the axle, and then there's also this pulley, and that pulley is attached to this hub right here that clamps it to the axle. And then the axle runs through the two plates and has bearings in each of the plates. And then the axle is constrained, which means it's not allowed to move back and forth with these shaft collars on the outside. And then if we go over to dead axle, this will load. Right. So you can see here that the shaft that's going through the wheel and the pulley is stationary, and it's held in place by these two screws. And then there's a bearing, if you can see right there, attached to that pulley, as well as one on the other side here. And then what this allows you to do is that the axle is stationary, but then the wheel can rotate around the axle versus the axle rotating the wheel. And then this is generally more robust than a live axle setup, just because the axle itself is just another standoff like any other of these other standoffs here. And then if I can load up a zombie axle, right, so we can see, so you can see here that the axle is allowed to freely spin because of the bearings on the outside, but the pulley is directly attached to the wheel. So, and then the wheel is clamped to the axle. So it's just small variations, but they're all generally the same concept. Okay, so now we can go to answering our question. So the first question is, how common are 8-wheel drives within FTC? So for tank drives and any type of drive system, it really depended on the game and what the game required. So and also just your robot design in general. So 1 second, let me bring over the questions. Yeah. So like for example, in Rover Ruckus, there were a few teams that opted to do a 6-wheel drive or a tank drive. So you can see that Recharge Green did this right here. And this was because they wanted to play heavy defense and be able to shove other robots that are using mechan wheels or omni wheels out of their way in order to have good cycle times and collect the minerals very effectively. So in terms of 8-wheel drives, well, again, it's all up to the team's preferences and needs. And how common, I haven't seen a whole lot personally. Usually people just do 6 wheels and that's enough for them if they were to do a tank drive. But I mean, if you want to do 8-wheel drive, then you can go ahead and do 8-wheel drive. What is your opinion on full custom versus hybrid versus full kit drivetrains? So again, it's all up to the team's preferences and what the team's resources, what resources your team has. So I know there are a lot of teams that go full custom, and that's because they have ready access to the CNC, laser cutters, water jet, all that stuff, just so that they can, so they don't have to like, and then their lead times are very low, so that they don't have to wait on getting these parts for their drivetrain. And then hybrid, so I think our team actually attempted to do the hybrid, as you saw with the, you can see here that we had to go build a pattern on our custom stuff, and we had this go build a channel here and whatnot. So this was because our lead times are very high, just because it's one of our sponsors who does the cutting for us, and it takes a little bit of time for them to cut out the stuff for us and then deliver it to us, just because obviously they have their own things to machine and whatnot. And then full kit, full kit is, again, just as viable as any other custom or hybrid. It just depends on what your team can do and what your team is best at doing. So all of them are equally viable. You can see here, this one was actually used by Recharged, who built this spot for Robo Ruckus. They used this drivetrain for Skystone, and you can see it's almost completely Go Build Up, and that's because they are sponsored by Go Build Up, so they get their parts for free or very cheap, and that's why they're more suited towards using the Go Build Up part system. So yeah, I mean, it's really up to the team and what they have access to and the connections that they have. And next is, what's your favorite CAD website? So the only CAD website, I guess, is Onshape, and that's because it runs on your browser. If you're talking about software, I've only ever used Inventor and a little bit of Onshape. I'm actually picking it up right now. So Inventor works just fine for all my needs. I haven't felt like I'm missing out from something just because I'm using Inventor. But then I really like Onshape, like how user-friendly it is. So I guess, so I can't really give a really definitive response to this because I've only used like one and then a little bit of Onshape. But I think Abid can talk about his favorite CAD because he's used a lot of programs.
Yeah, I've used all four, and honestly, I think that a combination of Inventor and Fusion is the best because like the collaboration part of Onshape is probably my favorite part, and the tools of SolidWorks is also great, but you can't really combine SolidWorks and Onshape, but you can combine Fusion and Inventor because you can import files between the two really easily. So two of them I think work really well together, and yeah.
Yeah, and what he means by working well together is that like there's certain file formats and then changing the file formats and then just being able to access the files between the programs. It's a little bit cumbersome for using for doing cross software stuff. But since Inventor and Fusion are both made by Autodesk, they really optimize this so that you could use both programs kind of easily together. But then general purpose like Onshape and all of them are great for general purpose. It's just if you want to mix and match, then some are more preferable than others. So how do you pocket? So in this presentation, we created Game Manual 0, and that's like a crowdsourced like introductory game manual that very experienced members of the FTC community have put together for rookie teams. And in that game manual, they have a tutorial on how to pocket. So you can look at that and then you can try it out. But if you're still confused, there's also the FTC Discord, and there are tons of people ready to help you if you want to learn how to pocket. So what is your favorite wheel? So last year we used those Gobilda mechanisms. They never failed. They work perfectly fine. Somewhat alternatives to that are the Nexus mechanism wheels, and Rev also has their own mechanism wheels. But I wouldn't say it's exactly my favorite. It's just more suited towards Skystone just because omnidirectional movement was very important or very optimal for Skystone just because like for intaking a stone or positioning yourself with the foundation in order to stack a stone. So it was pretty important to go with mechanisms. And then obviously there are teams that were able to use other types of wheels, but they had their own workarounds in order to have a very to have their own, like, again, I keep rambling, but it's really up to preference. So I guess my favorite would be the Gobilda mechanisms just because they always work. I had no problems with them, and they're just, and then and obviously they mesh with the Go Builder system, which is what we used extensively in our robot. So
Just another thing to add on top of that, they asked favorite wheel. One thing we didn't cover in the presentation because we were focused on drivetrains was the compliant wheel, which is very popular for intakes and other non-drive applications. So while we didn't cover them, I think we can include a link to them in the afterwards email, and that's also another wheel that FTC teams commonly use that rookies should look into.
okay, so what is the cutest type of drivetrain? I don't know. So I think, I mean, mechanisms are always cute, but like but then, uh, but six-wheel drives are also cute too, I guess. So what is your opinion on the new 19.2-to-1 strafer that is now possible to go build those miter gears? Okay, yeah, so I think that the miter gears were definitely a great addition to the Go Builder part catalog, and that since the strafer chassis, it used a 13.7-to-1 motor, and that was geared 1 to 2, so this meant that the final ratio is around 26 to 1. So this is like generally a little slower than you would like it to be. So I think now with the addition of those miter gears, that yeah, I think that 19.2-to-1 strafer chassis would be a great starting point for many rookie teams and or beginner level teams to learn how to learn the in and arounds of drivetrain design and have a very solid base to build the rest of the robot upon. Okay, next we have, can you explain dead axle again? Okay, so let me go to here. So I know it was a little confusing for our team at first to like really grasp like how this worked. So so there's a standoff going through connecting both sides of the pod as well as going through the wheel and the pulley. So but you still need the wheel to spin with very little resistance on that axle, right? So that's where introducing those two bearings on either side, on right here on the pulley side and on the wheel side. And what this allows you to do, so like if you can see my arm, that the wheel would just spin around instead of my whole arm spinning, the wheel would just spin around. So
you want to show them the animation on the left?
oh yeah, I completely forgot. Here, I have to right click this, or I have to right click something.
No, right click to animate. Show.
Right click. Show. All right.
Yeah.
See, I'm still trying to figure out on shape, so bear with me, please. Animate. There we go. Yeah, so you can see here that the axle itself is not moving, but rather the wheel is turning about the axle. So if you're still confused, then just ask the same question, and I'll try to explain it in a different way. So what was your drivetrain gear ratio this season? So if you can look at our drivetrain. So I know it's hard to see here, but we had these motors in the channel, and they were 19.2-to-1 motors. And then we had these 90-tooth gears, one on the motor and then one on the wheel. So they created a 1-to-1. So our final output would be 19.2-to-1. And then this is because just in case our bot needed to be heavier, we could still produce enough torque to still drive around and have a decent amount of speed. But also, like, our bot was very light, and this was because we wanted to be the best feeder that we possibly could. So, but then the 19.2 drivetrain was still fast enough in order to feed effectively. Did you run into any issues with gears? Do you plan on using them again this season, or are you looking at a timing belt / chain? So the only thing with gears is that they need to be well lubricated. and we did this using white lithium grease. And then no, we didn't have any issues with the gears. But the only thing that we would change is that if you can look at our design, these channels are almost on the outside edge of the robot. And then this inhibited us from having an effective compliant wheel intake. So the way we can solve this obviously is by moving the motors closer to the center of the robot and then having a timing belt or chain or whatever to transfer the power. So yeah, we are definitely looking into using belt and belt specifically just because of the low maintenance versus chain. So yeah, so we're definitely considering using belts, but we wanted to keep it simple for our first season, so that's why we went with just the geared 1-to-1.
One more thing I just want to add is that the one upside to gears is that if you use gears, your drive pods will be generally thinner than belt because belt is thicker. So that's just something to consider.
Yeah, that's true. Like these standoffs right here are they're 72 millimeters, but we could have easily gone with the 64 millimeters, so that would have shaved off like around 2 centimeters on either side of the robot, or on as a whole on a robot. And just are you going to 3D print your pulleys for the time belts? Yes, most likely we are, because not a lot of pulleys that you can buy commercially have those mounting holes that allow you to mount it to the wheel and give us that preferable dead axle setup that we used last year and was very effective. And that's because if you can look at the Mecanum wheel, or let me see if I can get a picture. Yeah, right here. So the wheel has those mounting holes on the ring, on the outer perimeter of the wheel itself. So you can see here those 4 wheels right there. I mean those 4 holes right there. And then then you would have to use a fairly large sized pulley in order to bolt it on, as well as you need those holes in order to bolt it on. So that's the great thing about 3D printing, is that it's very flexible and that we could get those holes right where we wanted to. So yeah, we're gonna be 3D printing our timing belts, and a lot of teams when they want to do timing belts do print them out. Any last minute questions that we can answer?
Don't be shy.
Okay, so now that we're done, it would be great if you guys filled out the feedback form that I think Heather will send, or it's already sent in the Zoom chat. So it'll be great if you guys filled that out, and then if you guys have any more questions after this, and if you wanted to ask us specifically, we're all very active on Discord, so you can ask us in the first online Discord, as well as the FTC Discord. And you can also shoot us an email at ftcteam16236@gmail.com.
I think that wraps it up. Thank you everyone for attending, and good luck next season.
Thank you guys.
Thank you.